As this memorable semester of ECH 4123 draws to a close, I wanted to make sure to leave some time left to discuss chemical reaction equilibrium. Just as a quick note, I really wish I had budgeted more time in the class to cover chemical reaction equilibrium because it is one half of the course title, right? It's phase and chemical equilibria. Unfortunately, I just got too carried away and had too much fun talking about Excel and deriving all those formulas from the phase part of chemical equilibrium. And also I'm biased because remember, the phase part is the stuff that is the fundamental basis for the class that I teach and that you'll take next semester, separations. This other part, this chemical reaction equilibrium, remember I described in the very first class period that this forms the basis of another class you'll take, which is kinetics. So just in general, when you're considering a chemical reaction, recall that there are two fundamental questions that you would need to consider or answer as the engineer. One is how far will that reaction go? And two is how long will it take to get there? These are two completely different questions that are sometimes related. So as I mentioned, question 2 is going to be the subject of your kinetics class, which you will take later on in the curriculum. Whereas question 1 was kind of already answered for you. So I touched on it very, very briefly in material and energy balances, and also it was touched upon in Gen Chem. Hopefully it was touched upon in Gen Chem. So hopefully what I describe is not completely new. But in phase equilibrium, I want to briefly discuss how you would go about answering that question more generally. And when I say that, I mean in a way that assumes no simplification. So as I'll describe to you in a moment, that answer to the question that we talked about in MEB and possibly in Gen Chem was oversimplified in that, like so many other things in MEB and Gen Chem, it assumes ideal conditions. So once again, in phase equilibrium, we'll talk about how to calculate the equilibrium constant in a way that does not assume ideal cases for either the ideal solution or the ideal gas. So let's start by just considering a very general reversible reaction where you have moles of A and B that you put into a reactor, and the forward reaction will react those moles of A and B into other molecules, C and D. And once you start making some C and D molecules, those molecules can then react with each other in order to form A and B again. So just some quick nomenclature notes where this curvy letter V, remember, is the Greek letter nu, and this is the stoichiometric coefficient. Stoichiometric coefficient. And remember the convention that I touched upon in MEB, which is also applicable otherwise. Negative for reactants and positive for products. All right, so for example, if I had 2 moles of A plus 3 moles of B that are reacting to form 2 moles of C and 1 mole of D. So if I had 2, 3, 1, I forgot what I said. Let's just go with this. 2, 3, 1, and 3. The stoichiometric coefficient for A would be -2. Stoichiometric coefficient for B would be -3. Stoichiometric coefficient for C is +1, and stoichiometric coefficient for D is +3. And as the engineer, you want to know that if you allow this reaction ample time to reach equilibrium, and once again, that ample time is a very nuanced question that requires some knowledge of chemical reaction kinetics, because that ample time could be seconds, it could be minutes, it could even be years. So it strongly depends on what the reaction is. But if you allow it enough time to reach equilibrium, what will your concentration in the reactor be? So say you start off with A and B, you let that reaction go until it reaches equilibrium. What will that equilibrium state be? So as a result that you may be familiar with, you would need to know what the equilibrium constant is, K of T. So the equilibrium constant, this is how it's denoted in the Dauman-Visco textbook. It just is a reminder that this value of K, the equilibrium constant, is only valid for a specific temperature T. So in Gen Chem, you probably learned that your equilibrium constant is proportional to the concentrations of your chemicals to the power of the stoichiometric coefficient. So an example, it's in general, right? It's pi of concentration of the chemical. So let's say Ci to the nu I. Right, so for this particular example, it would be, remember, stoichiometric coefficient is positive for the product, so those are on the numerator. So concentration of C to the new C power concentration of D to the new D power concentration of A to the new A power and concentration of B to the new B power. So once again, this is the GenChem equilibrium constant is what I'm calling it. And this is only going to be valid for ideal gases and ideal solutions. So you can draw an analogy to the ideal gas law. It's something that you learned in GenChem that is applicable if you can assume ideal. But again, in this class, so many times we very rarely assume ideal conditions. So how does this help you from a problem-solving standpoint? Well, if you knew what the value for KT was supposed to be, if you knew what the equilibrium constant was, so if you had that value, whatever it is, you could theoretically calculate the concentrations of all species involved in that reaction. At this point, you're probably confused because I just have written one equation, right? I've got KT is equal to this right-hand side up there. But it looks like I'm saying that you can calculate 4 unknowns, so the concentrations of the 4 species. So how is it that I can relate, or how is it that I can solve one equation for 4 unknowns? The answer to that question is that I don't really have 4 unknowns. Recall that I can express the concentration of all of these reactants in terms of the extent of reaction, and they're linked by stoichiometry. So just for example, by the stoichiometric coefficients that I've given in red for the example above, if I don't start the reaction with any moles of C or D, then I know that the concentration of D is always going to be 3 times that of component C. And I know that because they're produced in a 3-to-1 ratio, and they also react in a 3-to-1 ratio. So that is always constant. So by using tricks of stoichiometry, so this is also a good place to recall your material and energy balances. Remember extent of reaction balances and molecular balances and atomic balances. You could relate these concentrations all to a single parameter. Remember the parameter squiggle for extent of reaction. So once again, I'm not going to go through exactly the details. I just want to give you a quick overview of what the thought process is. You would relate the concentration of all these species to this extent of reaction, and then you would express CC, CD, CA, and CB all in terms of squiggle. And then if you had a numerical number for KT, you could calculate this squiggle, which would enable you to go back and calculate the concentrations of all the species. Now, in textbook practice problems, you may see sometimes that they would just come right out and tell you what the equilibrium constant KT is. But in real life, of course, it's not that accommodating, and the problem wouldn't just present itself and tell you, hey, the equilibrium constant is supposed to be this at this specific temperature and pressure. This is also something that you might have learned in Gen Chem class of how you would calculate what the equilibrium constant is. You can also relate the equilibrium constant by saying K of T is equal to the exponential of the minus delta G standard of reaction RT. So once again, this minus delta G standard, not the minus, but the standard Gibbs free energy of reaction. Standard Gibbs free energy of reaction is equal to the sum of nu I times the molar standard Gibbs free energies. This is also something we touched on at the very end of MEB. So just as an example for the reaction that I gave above, where I have nu A plus nu B, and so forth, my Gibbs energy of reaction standard would be equal to nu A Gibbs energy A standard plus nu B Gibbs energy B standard plus nu C, where remember again that the stoichiometric coefficients can be positive or negative. GC standard plus nu D GD standard. And these standard Gibbs energies are for the specific compounds at the reference state. So I'm just going to make a quick note of that. And practically you could calculate these standard Gibbs free energies by taking or looking up the standard Gibbs free energies of formations. So again, something that we covered in chapter 9 of MEB that I'm only briefly covering just to show you what the thought process would be. Now, for our purposes in phase equilibria, The way that we'll extend this is I'm going to, again, skip the derivation. I'm not so much worried that you know what the derivation is, but give you a practical way that you can have an equation that you can use to apply to a non-ideal situation. So this is the equation that you would use in order to relate or to find the equilibrium concentrations of all your things. The first equation, KT is equal to the exponent of minus the standard Gibbs free energy of reaction over RT, is the same as you learned in your Gen Chem class. That has a theoretical basis behind it that I'm going to skip in the interest of showing you how to apply it. But the last part is pi. So this is, or pi is not a symbol, it's a mathematical operator, which means you multiply the things together. So I introduced that. The analogy here is above when I said that the, where is it? K of T is the multiplication of all the concentrations times the stoichiometric coefficients. The way that you would apply that for a non-ideal situation is by taking the ratio of the mixture fugacity to the pure component fugacity at the reference state. So just for completeness, I'm going to annotate this equation with a meaning for all the variables. So just to review, K of T is the equilibrium constant at temperature T, at which the reaction is occurring. T is obviously the temperature. Delta G under bar of reaction standard is the change in standard Gibbs free energy upon reaction at temperature T. F hat of species I is the mixture fugacity of species I, and F naught is the fugacity of pure component I at the reference state. So that at the reference state is important. And I should write it more consistently. It's the fugacity of species I standard, right? Not necessarily, this is not a zero, by the way. This is the naught sign for, I sometimes say zero, but it means standard in the notation. So next, I'm just going to show you that for ideal cases, this equation cancels to what we're used to. So an example, for an ideal reaction, or for an ideal mixture, ideal vapor / ideal mixture reaction at the reference state. Remember, if your reaction is not at the reference state, then you have some additional steps to take. At reference state. So let's say we've got the reaction A is, the reversible reaction is going to B plus C, and the reaction is occurring at 25 C in 1 bar. I would say that the equilibrium constant, K of T, is equal to this first term, the exponent of minus delta G standard R over RT. We're going to assume that we have that numerical value. How would I evaluate the right-hand side now? It would be the product of the mixture fugacity divided by the pure component fugacity standard to the stoichiometric coefficient. And for this particular reaction, my stoichiometric coefficients are as follows. For A, I have -1, for B, I have 1, and for C, I have 1. So it's going to look a little bit simplified, but remember that there is going to be an exponent, but because it's going to be a 1, you won't be able to necessarily tell. So I would have the mixture fugacity of A divided by the pure component fugacity A standard to the first power, multiplied by mixture fugacity of B divided by pure component fugacity B to the first power, all over, oh, I'm sorry, wait, A is -1, right? So it's FB over FBs. So I need to change these to C's. And A is in the bottom. FA standard to the -1, but it's in the denominator, so the sign gets flipped. And if we're assuming an ideal gas mixture, which is reasonably appropriate for 1 bar, so for ideal gas, and this is appropriate for low pressure, for P is equal to 1 bar, which is low, I can say that the mixture fugacity for species I is simply equal to the partial pressure of species I, which is equal to yi times the total pressure. And furthermore, if we assume that it is an ideal gas and we have a low pressure, then my pure component fugacities are just simply going to be equal to the pressure, the total pressure. So I'm going to write that as the reference pure component fugacity. That's Fi naught is equal to P naught, which is the reference pressure. And if my reference pressure is 1 bar, which numerically having it be equal to 1 means it's going to cancel out, or that it's going to, you just don't even need to write it. So in my example here, it's going to simply simplify to, again, I'm going to write everything out in extreme detail, even though it's kind of trivial. YB times P over P times YC times P over P over YA times P over P. All the P's are obviously going to cancel, and I'm going to be left with the mole fractions, which mole fraction is another way to, a more convenient way in this case, to denote what the concentration is. Now, what if I could not assume ideal? So let's say, for example, this same reaction is carried out at 10 bar. How would things change? Well, for one, I would need to know what the reaction constant is for 10 bar. So in general, the reaction rate, or the equilibrium constant, I'm sorry, not the reaction rate, that's something completely different. This K of T is a function of pressure as well. Whoops. I would need KT at new pressure. So I'd need that numerical value, which I could calculate, or hopefully hope it would be given to me in a problem statement, but in a real engineering context, you would have to go out and recalculate it. And you would also need to then calculate the mixture fugacities. Need to calculate both the mixture fugacities and the pure component fugacities. And pure component fugacities. For each, and then you would just simply use this equation. Now I say simply, this is not a simple problem, right? So this is where I really wish we had another week to devote to this to actually do some example calculations, right? But the calculation of fugacity would require an appropriate equation of state. So it requires an equation of state in EOS. And it would require those fugacity equations that we've seen multiple times that you don't have to know how to solve, but you would have to know how to calculate them once that equation is solved. So just for example, for Peng-Robinson again, I'll write it out. So remember this equation, this would be an equation that you would use to calculate what the fugacity is using the Peng-Robinson equation of state. Or there's analogous expressions for the other equations of state. But this problem would then require that I calculate the fugacity for each component at that specific temperature and pressure. I think I'm getting too detailed now. This is kind of all I wanted to say about chemical reaction equilibrium. I hope you found this instructive, even though I'm not going to necessarily emphasize this in the class. Hopefully it gives you the necessary background that you need. With that, I'm going to say that the material of this class has concluded. And what I'm planning is for next Monday, I want to do a review, and I will hopefully post that review video no later than Monday morning. And I'd like you to watch that video by Monday's class. And then at Monday's class, we'll have the synchronous session will be totally dedicated to review for that exam that will be posted on Monday evening. I'm still planning to have synchronous class Monday and Wednesday of next week, even if there's not much to talk about. And we'll kind of discuss how the semester went. And I'm looking forward to seeing you then.